I think we should start.
Great.
Okay. All right. So welcome, everybody. This is the first Spiral seminar in a very long time since the pandemic shut everything down. I'm really glad we've resumed the seminar series, and I'm very pleased that we have Akil Narayan to kick off the series. So I've known Akil, I don't know, for a few years. I don't know how long I'd heard that he joined I worked with the University of Utah some time ago, and I knew that he worked on an area that I've been interested in for a very long time, which is thinking about how to approach the kind of biophysical modeling and then inverse solutions and optimization that I'm interested in from a point of view of thinking about being able to incorporate uncertainty, about particular uncertainty, in my case, about parameters of the model into what you do. And more recently, I've gotten involved in a project with Akil and my colleague Rob McLeod in Utah, specifically to build some software to compute certain ways of approaching this modeling of uncertainty in these models. And I can say with without equivocation that pretty much every time I have an interaction with Akil, especially when we talk about anything technical, I learn things. I have high expectations, Akil, not to put any pressure on you for this seminar, because I feel like you just have you're really able to explain things describe things in a way that's really clear and lucid and thought-provoking. So without saying any more, it's my pleasure to introduce Akil Narayan.
Thank you, Dana, for that wonderful introduction. Yeah, no, the interactions that Dana and I have been, I think, very productive for both of us. And a lot of the work that I do dabbles around in UQ, uncertainty quantification. So that will be the topic of what I'll discuss today. I would like to thank the organizers, Kimia, Dana, for inviting me. And I guess since this is the first talk of the seminar series this semester, or this year, maybe, I feel absolutely no pressure whatsoever to not screw it up. So we'll see how it goes. I am trying to keep an eye on the chat. So if there are any questions that you want to type out, please go ahead. I'm also comfortable with you just unmuting yourself and asking, assuming that's okay with the organizers. So we'll try to keep an open mind about this. This is joint work with a lot of people. So I think you can all see my mouse and the laser pointer around it. Yeah, lots of people, both senior to me and junior to me. So this is the work of a lot of people that I'm going to try to summarize in a little bit of time. I'm going to aim for about, I think, 45 minutes. And so that way, if we can have time for questions or discussion if there are any. I come primarily from a world where fluid dynamics and solid mechanics are king. And so a lot of the examples that I'm going to talk about come from that particular regime. So the title here has a lot of buzzwords. I'll start by trying to motivate what I mean by these multi-fidelity problems. So let's get straight into it. And I have to figure out how to advance the slides. All right. At least at a high level, the idea of multi-fidelity is that, well, in this particular case, I'm going to simulate airflow around at least the 2D silhouette of a wing. And I'm interested in prediction of some sort. So I just want to send a flow in and see what happens, for example. In this particular case, I might care about the lift or the drag coefficient on the wing. And so we think of this as a forward simulation. I'm going to input, say a forcing function. I'm going to do, in this case, what looks like a finite element simulation on this domain, and I'm going to get an output. And I'm going to treat that forward model process as a black box in pretty much everything that we talk about today. We'll go through a lot of examples of forward models, but I'm still going to treat them as black boxes. Now, the multi-fidelity problem is that, well, okay, I could do a very expensive simulation on this very refined mesh on the right, and presumably that would take a lot of time. And I can do a simulation on the left mesh, which is, of course, much more coarsened, and we expect that it's not really going to be a good representative of the truth, the ground truth. But the question is, can I still use maybe coarsened information about the prediction on the coarse scale to tell me something about what I really care about, which is accuracy on the fine scale. And I'm not just going to want to do this for a single forward simulation. I want to do a parametric version of this. So the inputs to this, which can be angle of attack of the input wave, or even geometry of the particular wing that I have here, these can be parametrically varying. So I might parameterize the angle of attack. And then I might be interested in, for example, the maximum lift coefficient or the largest drag coefficient or something like this over that regime. And so really what I care about are parametric versions of these potentially expensive forward models. So I'll give you another example, one that has a little more details now with this. That is, in this case, stenotic flow. So this is a simulation with a high-fidelity model on the left, which is Navier-Stokes, and on the right is a simplified model, which is a linearized version of Navier-Stokes. And in this particular case, I am asserting that I'm interested in, say, the flow at the outfield as a function of a parameterization of the stenosis. So I'm going to have a parameter that wiggles around what the stenosis looks like. So here's one realization of the parameter, and here's another one. And I would actually like to get predictive information about these Navier-Stokes forward models, but I'd like to do it somehow using these cheaper models. And of course, I'm going to have to make a trade-off here. I understand that the cheaper models aren't going to give me the correct forward model, but they probably give me a reasonable guess of what's going on. You can make an argument that that's not true based far in the tail here, because obviously these things look very different. But the point is that I might be able to get macroscopic large-scale information from the low fidelity model, and it might be a lot cheaper to do this. All right. Normally, I have the thumbnails of slides, so I know it's coming next, but I don't remember what's coming next and I can't see it, so we're going to be surprised together. All right, this is, those were two examples of what multi-fidelity means, where I have a coarse and a fine scale model. In a general setup, I might have a class of forward models, which I'm calling U1 to U, well, U infinity, I suppose. I don't have a terminal one. And I'm going to assume, at least in the notation of this talk, that as the index increases, the accuracy increases. So things get more and more expensive, but also more and more accurate as I increase the index. And they have different degrees of freedom, right? So in the finite element simulation and in the airflow model that we had, obviously the number of mesh nodes is different in the coarse model than the fine scale model. I'm going to simplify things for the purposes of this talk and assume that the parameters that I have, which I'm going to call mu now, so mu would be something that controls the stenosis in the Navier-Stokes example, or something that controls angle of attack in the airfoil example. And so I'm going to call these parameters mu, and I'm going to assume they're Euclidean in d-dimensional space. And more importantly, actually, I'm going to assume that all of these models depend on the same parameter. This is actually the most restrictive assumption that I'm making in this particular talk. We have ways of relaxing this, but at least to make concrete mathematical statements, we kind of need to have the same parameter. I've given you two examples that shows you sort of a variety of things that multi-fidelity might mean. In the first example, it was mesh parameter, excuse me, or type of numerical discretization. So how many finite element elements I had in a triangulation. But I also try to convince you that we can talk about more general cases. So in the stenotic flow example, the linearized Navier-Stokes and the full Navier-Stokes could have the same degrees of freedom, same number of degrees of freedom. It's just that the full Navier-Stokes is more complicated and difficult to solve. So I might actually simplify physics in this particular case. And there are, there's a huge laundry list of possibilities here in terms of what you might mean by multi-fidelity. We'll go through a lot of examples in this talk, time permitting, I guess, but yeah, there's a lot. So anyway, as you might expect, the way I've set up this problem, or at least the way I've posed this problem to you, this sounds very difficult. It should sound very difficult anyway. For example, I claim to have set up the case where, so the forward models, what I'm calling the state predictors, the forward models don't necessarily predict the same thing. And that might not just be that they don't predict, it's not like the low fidelity model necessarily predicts a coarsened version of what the fine scale model does. It might actually predict something completely different. And we'll go through a couple of examples of that later. Of course, in the way I set up this problem, I said, look, I have a lot of predictors, and I'm going to tell you exactly how the cost and accuracy varies. As I increase the index, I'm going to get something more expensive and more accurate. But in reality, you probably don't have this, or you might not have a very clear hierarchical ordering like this. And for the purposes of this talk, I'm just not going to talk about these difficulties. I'm mostly going to care about maybe the first bullet point. And that's because we can say something concrete, and there's already enough to talk about with that. Okay. All right. So again, really the goal here is at least to simulate a more expensive model at the cost of a least expensive model. So I'm looking for a free lunch. And of course, I'm not going to get one, but we can talk about how we can get close. Well, the punchline is that we're going to get at this goal of simulating more expensive model by looking at a cheaper model by looking at low rank structure. Okay, and so the punchline, the theme, if you remember nothing else from this talk, is that basically what I'm going to do is I'm going to look at a cheaper model and figure out a way to extract low rank structure from the cheaper model. And I'm going to use that knowledge of a low rank structure on a more expensive model. That's the entire punchline. Okay, and so I'm going to spend the next, whatever, 30 minutes explaining this to you, or explaining how we do this anyway. So there are lots of other multi-fidelity methods. I'm not going to talk about any of these methods, but they exist. Some popular ones are things like multi-level Monte Carlo. This is actually not the seminal reference. I'm not sure why I chose this one, but anyway, multi-level Monte Carlo. There are multi-level GPs. You can do all sorts of crazy things. So I do want you to understand that there is a broad world out there, and I'm really just going to talk about one strategy, which is low rank approximations. And what this means, what does low rank mean? Well, it actually means something very specific, which is that I'm trying to leverage reduced order properties of what I'm going to call solution manifolds. And we'll give a little bit more background on this. But this is really the key to what we're doing. We're going to assume that these models have hidden low rank structure, and we're going to try to find that hidden low rank structure. And that's going to be easier to do on a coarse low fidelity model than it's going to be on an expensive high fidelity model. And so that's essentially the entire selling point. Okay, so I'm going to spend the next, I have the next X number of slides that talk about reduced order properties. I'm going to try to leaf through these as quickly as possible. This is a very large presentation, so I'm not going to go through all the slides carefully, but I'm just going to warn you right now that the next few slides target specifically trying to convince you about low rank structure. And I'm going to go through them fairly quickly and skip a lot of them because some details we don't need to care about. Okay. So what are low rank approximations? Well, low rank approximations essentially try to find, they try to predict variability with respect to a parameter, which again, I'm calling mu, in a small dimensional space. That mostly is what a low rank approximation means. And so again, my notation here is that mu is a parameter, and unfortunately the very similar looking u is the forward model. So u of mu, they both look and sound similar. That's an unfortunate choice I made, but here we are. And so everybody here, I'm sure, knows low rank approximation by one of a variety of alphabet soup names. So proper orthogonal decomposition, principal component analysis, singular values, eigenvalues, reduced basis methods. These are all shadows of the same idea. We're simply going to try to compute in the PCA case, eigenvalue low rank structure. So here's a particular example I'm going to show you. This is a bit of a wonky one, but just to show you how general this can be, I'm going to solve a pretty simple Laplace equation raised to a fractional power. And so there's a way to define this mathematically. And so my parameter is actually the order of the Laplacian. And so, of course, when the parameter mu equals 1, I have standard Laplace's equation. When mu equals 0, I have an identity map. And so we have different reduced order properties for this. And the point really is that even for this kind of crazy looking example, as a function of the number of degrees of freedom, the solid lines are what's important for this plot. You can see that you get pretty good error. It looks exponential-ish. Okay. And so even for a fairly complicated model, I know this is not in a complex geometry. This is a 2D example. But in any case, I can actually get a reasonable approximation instead of using a very refined mesh, which is the high fidelity model. I'm going to use, let's say, 10 degrees of freedom. So that's capital N, that's my 10, and 10 degrees of freedom gets me pretty good accuracy relative to the high fidelity model. Okay, that's the idea of low rank approximation. In particular, what I'm doing here is I'm forming my emulator, my reduced order emulator, as a linear combination. So these CNs are just constants. These are linear combinations of snapshots. Right? So I'm going to pick different values of the fractional order. I'm going to solve the expensive high fidelity model, and I'm going to linearly combine those to predict the forward model for any other value of the parameter. Okay, that's it. That's essentially the entire idea. And again, the hope or the goal is that I can do this with a number of degrees of freedom that's a lot smaller than a fine scale model. Okay. My goal is to not get bogged down in too much math, but let's look at one more example, which is maybe more interesting. Here's a 3D example of a sort of parameterized, this is 3D Laplace's equation with some crazy diffusion, and there's a reaction term sitting out back as well. So the parameter here is actually two-dimensional. Here's a snapshot of what the solution looks like. And here, this plot is showing you speed up. So speed up of the reduced order model compared to the full order model as a function of the notation has changed here. Lowercase n is the number of degrees of freedom in the reduced order model, and calligraphic n here is, is the number of degrees of freedom in the high fidelity model. So the point is that both as you say refine the fine scale model and as you take say a larger number of degrees of freedom in the reduced order model, you still get several orders of magnitude speed up for this kind of approach. Here is just a geometric description of in the two parameter space. Remember, I'm taking snapshots at different parameter values. Here's where the parameters are located, just pictorially. And again, we get actually pretty good error. And more than that, for nice problems like this, we actually have error estimates. So we can prove things that show that, of course, the only way I can compute an error is if I know the exact solution. Of course, I don't want to do that in reality, but we can compute an error estimate that doesn't require the exact solution that rigorously bounds the actual error. So these methods are pretty strong. You can do a lot of nice things with them in this respect. Okay, so that's that. There's a lot of math coming up, and again, I'm going to warn you now, I'm going to skip most of it. I'm just going to reveal the whole slide, and I'm going to point out what's important. If you have a stomach for it, go ahead and try to read everything. But really, the point that I want to make is that you can formulate this problem generally. I can talk about a general mathematical model that has an unknown, essentially, prediction given by an input parameter mu. And then I can wiggle mu around in all the possible values that it takes. And if I wiggle mu around in all the possible values that it takes, this traces out a collection of solutions in some Hilbert-Banach manifold space, whatever you want. And so this is what I mean by the solution manifold. It's essentially the span, not the span, that's the wrong word, the collection, the set of all solutions to my forward model. Okay? And there's a mathematical way to talk about the rank of that manifold. This is called the Kolmogorov n-width, and okay, there's a fancy formula, but really the point is that if I make this number small, that means that I have a low rank representation. Essentially, this dn tells me something about the error that I make by approximating the solution manifold with capital N degrees of freedom. And so in fact, if you define all the spaces appropriately, dn is something that I think we all have lots of intuition about. It's a singular value from a matrix. So this is just a fancy way of defining singular values in fancy math spaces, okay? But the idea is simply that. It's just low rank approximation, okay? It turns out that you can make lots of fairly general statements about this. Again, I'm not going to go through details, but the point is that the decay, so how fast singular values, or n-widths in this case, decay as n goes to infinity, we can actually prove things in some cases. And in particular, we can prove things using a very popular model that lots of people use, where this thing is actually a random field. So the diffusion coefficient is a random field. And we can talk about how the n-width decays, and we have estimates, blah, blah, blah. Okay. So really what you should be asking is that, okay, I've tried to convince you without going through details that there's a mathematical foundation for this, but the real question is, how do I actually realize this, right? How do I actually find this low rank space? If you remember the formulas that I had in the previous slides, they had things like supremums and infimums and stuff like this, and you're never going to compute these in reality. So how do we actually get our hands on something? And it turns out what most people have agreed on, again, with a lot of background in theory, is that a great way to do this is in a greedy way. Okay, and what does greedy mean? Well, it means, remember, I'm trying to find snapshots, so I'm trying to find parameter values. And the one that I'm going to pick is the one that commits the maximum error at sorry, I didn't set it up right, but one that commits the maximum error relative to my current approximation. So this subspace is the span of the previous snapshots that I have. I'm going to try to find the best approximation, and the guy that commits the most error I'm going to pick out. Okay, so that's a greedy approximation. And this doesn't do this crazy inf soup inf things, but it gets close. And we can actually show that with weak greedy algorithms, you can get close. And so weak greedy algorithms appear everywhere in computational science. Even something as simple as linear algebra factorizations that we all use, these are greedy algorithms. So pivoted LU decompositions and pivoted QR decompositions are greedy algorithms, it turns out. So, so there's a lot of math behind all of this. But the point is that the computational strategy for finding this low rank structure comes from greedy algorithms. And that's really the main point. Okay, so, well, I'm giving away the punchline, but why did I go off on this 10 or 15 minute tangent to talk about low rank structure? Well, the reason I went off on this tangent is that, well, I'd like to find a reduced order model for, generally speaking, my prediction. And I'm going to do that by computing an error estimator, which I'm going to use in a greedy computation. Okay, so I actually want to use this in my greedy computation. Of course, again, this thing explicitly assumes that I can compute the solution. You can come up with an emulator for that as well. You get a weak greedy algorithm, and that works. Okay, now, if I were doing this in the high fidelity regime, if I only had one model, this would be the entire story. The story would be, okay, I'm going to lay down my problem. I'm going to try to find an error estimator for a low rank approximation, and I'm just going to do greedy approximation on that ad nauseum. And well, the punchline in this talk is that, well, if you're in a multi-fidelity situation, you have a cheap and expensive approximation to the high fidelity model. It's the low fidelity model. So instead of banging my head against the wall and trying to figure out what a good error estimator is for this greedy procedure, I'm going to use the low fidelity model. Okay, and again, that is essentially the punchline. That's the entire game that we're going to do. And these expansion coefficients, CN, we'll also talk about how to compute those. Okay, right. So that's the background for low rank approximation. And finally, after 29 minutes, we're going to get to the table of contents of this talk. And I'm going to skip most of these bullets because some of them are mathematical, and it's, you know, I can tell you the punchline without showing you the math. But what we're going to spend the next few minutes on is actually a more detailed description of what I'm proposing. So I'm actually going to run you through an algorithm that shows you exactly what's going to happen. And then probably we'll have time to get to a couple of simple examples, and maybe we'll jump to the end to talk about some ways you can use this in design and optimization. So we'll see. It depends on how time goes. Okay, maybe any questions or things that come to mind right now? Okay. Well, I think this is more easily explained with the picture. Here is the entire algorithm. I'm showing you exactly what's going on. So there are two rectangles here. The left rectangle is a spatial mesh. So I have a coarse mesh, a low fidelity model, and a fine mesh, a high fidelity model. And this other square here is not the same. This is parameter space. So this is mu space. So again, mu is, for example, a box in this case. And what I'm going to do is that on the low fidelity model, I'm going to query a bunch of sample points, and I can do this. So every time I query a sample point, that means solving, say, a finite element model on this coarse mesh. Oops, and it gives me, you know, some field at the output. And I'm going to argue that I can do this. I can put a lot of points and get a huge collection of things like this because the low fidelity simulation is cheap. So I can do this. The second step is to say, well, I have this discrete manifold of solutions. Sorry, I keep highlighting things. How do I do a subset selection? So I have 1 million snapshots here. I'm going to choose 10 of them. And at least the way in this flowchart, I'm saying I'm going to choose these 3, at least this one, I should just use the numbers here. I'm going to use 3 out of the 10 or something here. So the way I choose these 3 is going to be with linear algebra, in this case, a matrix interpolative decomposition. But you can use, I'll show you, we can do other fancy optimization schemes, that's fine. But I can choose an important 3 set of snapshots, and these correspond to parameter locations in parameter space. And now the idea is fairly pedestrian. I'm going to say, well, at the low fidelity model, I've identified what the, say, important parameter points are. So I'm just going to close my eyes and hope that this is true in the fine scale model. So I'm going to just choose the same 3 points on the fine scale model. I'm going to get different simulation snapshots. So this is the most expensive part. I'm going to run my high fidelity model 3 times. And okay, this picture is meant to convince you that in fact, this is a smoother, a more refined version of this guy. So yeah, it looks like that. And once I have this small, in this case, set of 3 snapshots, I'm just going to linearly combine them for a general prediction at a new point. Okay, that's the pictorial description. Here's, now I'll show you a few examples, or sorry, a few equations with this. So to make everything concrete, we'll just do 2 models, low and high, so UH and UL. And again, I'm making the assumption that the error that the low fidelity model commits is a lot bigger than the error that the high fidelity model commits. On the other hand, it's also a lot cheaper. Okay, and the number of degrees of freedom can be arbitrary. It doesn't really matter. And an important thing here is that I'm not doing lifting. So in computational science and finite elements, in lots of kinds of simulations, you can do lifting procedures where you spatially, say, agglomerate to go from a fine scale model to a coarsened model, or you do a prolongation where you take a coarsened model and you project it or you lift it onto the fine scale mesh. I'm not going to do that at all. Okay, so I don't care about the geometry of the low and high fidelity models. I actually don't use that at all in what we're going to do. Okay, so I have a low and a high fidelity forward simulation. Again, what's the goal? The goal is I'm trying to get an error as a function of cost, where a multi-fidelity strategy beats simply banging my head against the high fidelity model. Okay, so that's the goal at the end of this. This pretty picture is an example that we're going to come to later, so we'll keep that there. So I've already revealed that what I'm actually going to do is a low rank approximation. So I'm going to approximate my high fidelity model with something called U star. And it's just going to be a snapshot combination of high fidelity snapshots. And I'm going to hope that I can take n, capital N, to be fairly small. Okay. The only thing that's changed from my low rank approximation tirade is that now, instead of using my knowledge about the high fidelity model to choose the important parameter points, I'm going to choose them greedily from the low fidelity model. And another thing that's changed is that normally I would take these C sub n's to be some basically projected version of the high fidelity model in a least squares sense, Galerkin or something like this. And instead, I'm just going to compute them from the low fidelity model. Okay, and of course, I want this to be a good emulator, right? So that's essentially the whole idea. What's the computation look like? Well, remember that in the high fidelity model, this would be what I want to do in terms of computing the important parameter locations. I'd like to choose the next parameter point to be the difference, well, to be the location, which maximizes the error between my forward prediction, the high fidelity model, and my low rank approximation, right? That would be what I want a greedy strategy to do. I'm just going to replace this norm on the inside with stuff that only depends on the low fidelity model. Again, I'm literally sort of closing my eyes and just changing the H's to L's. Okay. And the reason why this is useful now is that, again, this error, well, this norm is easy to compute because U sub L is very cheap. So I can do this. And so, for example, if you do this in 2-dimensional parameter space, you get a bunch of selections of parameter points. But this function, this norm L thing, oops, sorry, is essentially this contour plot here. So I'm looking for the maximum value of this contour plot. Okay, so but I can do this at least in principle because U sub L is cheap, so I can certainly do this kind of optimization.
Akil, are you optimizing over C sub J, or do you have some other way you haven't told us yet to get the?
I have some other way I haven't told you, and that's coming up next. Yeah, right. Exactly. So I'll spoil the surprise. It's literally just the least squares projection of this onto the span of the snapshot. Okay. So that's all. And in the low fidelity case, so of course I can compute those as well. Okay, so to follow up on what Dana just asked about, how am I computing these least squares coefficients? Well, there's basically a gram matrix, which is the inner product between snapshots on the low fidelity scale. And there's a right-hand side vector, which is the inner product at a given value of mu with the snapshots. So this is all just linear algebra, taking inner products at the low fidelity model. And I'm just going to compute a least squares projection. That's this. This is just the normal equations, basically. So there's nothing more than that. oops, okay. And really the point to make here is that this is how I'm going to choose these greedy points. And this requires me only staring at the low fidelity model. I'm not touching the high fidelity model at all. I'm really just staring blindly at the low fidelity model. And that's kind of the point. But these CN coefficients in my high fidelity emulator are going to be the same guys. So these are exactly the same coefficients computed at the low fidelity scale. Okay. I think there's one more here. Let's see. Again, I can't see what's coming up next, so I don't remember what my point is. But how would I evaluate this thing? Let's run through how it goes. So to evaluate this, well, first I need an offline stage where I compute the capital N snapshot, or the important parameter points. Okay, so that requires me to do a lot of heavy analysis on the low fidelity model, do this greedy search, blah, blah, blah. Then I identify these important parameter points, and then I take a bunch of time and simulate capital N snapshots of the high fidelity model. That's an offline stage. The second step is an online stage. Now, in order to evaluate this emulator, all I need are these coefficients. And to compute these coefficients, I go stare at the low fidelity model. I do one low fidelity model evaluation. I do a least squares problem, and that's how I get these numbers. So that's the entire procedure. It seems kind of naive, and it is. It turns out to work reasonably well. Some remarks here is that this should smell very familiar if you do GPs. This is very similar. In fact, it's almost the same as what GPs do. And you might say, okay, well, this really should only work when the low fidelity model and the high fidelity model are similar, when they provide similar forward predictions. The surprise is that that's wrong intuition. This actually works even when the prediction furnished by UL and UH is completely different. What we actually need is that the parametric variation, the variation with respect to the parameter, is similar. That can be very different from the actual predictive validity of the low fidelity and high fidelity models. Okay, and I'll show you a couple of examples, some of which, at least when I first saw them, they boggle my mind that this works in cases where you don't expect it to do anything reasonable. Throughout this talk, almost entirely, yeah, definitely we don't have enough time. I'm gonna use just this inner product as a kernel function. This is how I formed the Gramian on the previous slide. You can actually do this with any other kind of reproducing kernel, and then you can port in a lot of machine learning techniques for kernel learning and stuff. And so that's a chunk of slides here that we won't get to, but you can do this. Okay, so here's a flowchart, and I probably should have had this up while I was talking about the algorithm, but essentially, again, there's an offline and online stage. The offline stage actually requires me to do a lot of heavy analysis on the low fidelity model and then query the high fidelity model capital N times. And then in the online stage, if I actually want to evaluate this thing, all I need is to query the low fidelity model once, and the rest is cheap linear algebra. So that's more or less the idea. And yeah, there are lots of nuts and bolts that, whatever, it's fine. So I think in the remaining time, we're basically going to go through examples. So I'm going to give you a really simple example first, just as a sanity check. So at least I'm a mathematician. So when I come up with a crazy idea, I definitely do a sanity check first. And then I'll probably jump to something like these a posteriori analyses, and then maybe a couple of more examples, and then we'll end there. Okay, so here's the sanity check. This is not a real interesting problem. This is just a sanity check. So here's an arbitrary function as a function of space X, a parameter mu, and I'm going to call this other parameter epsilon, which is essentially going to be a discrepancy parameter. I'm going to form a high fidelity model that uses epsilon not equal to 0, and the low fidelity model is going to be epsilon equals 0. Okay. And so you would expect, okay, so epsilon, essentially when epsilon is 0, it has no effect. When epsilon is bigger, it quadratically modulates the frequency of this sinusoid. And so you'd expect, okay, when epsilon is large enough, then this procedure gives me nonsense. And that's what the right-hand plot is meant to try to convince you of, that the error of this multi-fidelity procedure, as epsilon gets bigger and bigger and bigger, gets larger and larger and larger. Okay, so good. Things make sense. Second thing that makes sense is that, well, I'm actually going to do a spatial refinement. So this capital K here actually controls spatial refinement. And so K essentially is smaller than 100 in this case. And again, what you expect is that as I coarsen my mesh, when K goes down from 35 to 15, I should get worse error. And again, sanity check it, that does exactly what it seems like it should. Okay, so that was just making sure that everything's fine, that everything looks okay. What I didn't do in this example is I didn't actually plot. So for example, if we take this epsilon 10 to the minus 3 example, which commits an error of 10 to the minus 5, say, I didn't show you actually snapshots, so the low and high fidelity snapshots. I should have, unfortunately, but what you'll see is that the snapshots actually look completely different. So the low and high fidelity snapshots don't look the same at all. But that doesn't really matter. It's not that the snapshots look the same. It's that as I wiggle the parameter around, I need that to be similar. Okay, that's really what matters in this context. Okay, let's see. There are lots of other toy problems. Let's not go with that. You can do this. Sorry, I know this is flipping by and you can't really understand what's happening, but you can do this in more complicated situations. So here's a 2D elliptic PDE with the parameterized diffusion coefficient. It's so-called Carhoon and Luva expansion, taken from an exponential covariance function. This is in 17 dimensions, so I actually have 17 parameters here. And the point is that, okay, well, I have 3 models here. I'm actually going to show you what we call tri-fidelity. So this is a very strange problem. So in the low fidelity model, I'm just using a 1D approximation. So literally, this is a 2D problem. I'm just going to squish it to 1D, and I'm going to solve a 1D problem. Okay, and again, from like sort of, you expect to get maybe general consensus in this case between the low and high fidelity models, but this is really throwing away a lot of important information. On the other hand, I'm going to construct medium and high fidelity models that are 2D models with finite elements, and they have different degrees of freedom, blah, blah, blah. The point is that for this slide, it's the solid curves that matter. The dotted curves are for a competing method. So we're comparing in this thing, but the solid curves are the ones that we care about here. And the point is that, well, if you're smart about bifidelity or you use tri-fidelity, then you can get pretty good accuracy. Okay, so this works in reasonably high dimensions. We can do things on acoustic horns, same idea here. There are 8 parameters. This is Helmholtz equation. Okay, I think we've covered this, so I'm sort of gonna skip over that. This is one that I really like. I really like this example. So this is just a bifidelity problem, 2 models. The top one is the high fidelity model, which is a meshed beam that I'm going to displace by pushing down on it with a force Q. So there's just a hanging beam that's hanging on a wall, and I'm just going to push it down, and it's going to deflect the beam a little bit here and there. And what I care about is the displacement as a function of X, and that displacement is what I'm calling U. Okay, and there are some parameters that are listed here in this table, but this is what the high fidelity mesh looks like. Okay, it's a fairly refined mesh. The low fidelity model is going to be something from first semester Euler-Bernoulli beam theory. I'm literally just going to say I'm going to smush this to 1 dimension, and I'm going to pretend that the displacement behaves like a quartic function. So this is the low fidelity model, which is embarrassingly easy to evaluate. And as you might expect, also embarrassingly wrong. It really doesn't give you the right displacement at all. The surprise is that if you use this multi-fidelity method, sure, the low fidelity displacement, this is just a quartic polynomial, doesn't match the high fidelity simulation. But if you use this bifidelity reconstruction, you actually get pretty much the same thing. And again, the way I got this dashed yellow curve is I said, I'm just going to stare at how the wrong model behaves, and I'm going to use that to find low rank structure. Okay, and this works surprisingly well in this particular case. That you can actually extract low rank structure from a high fidelity model by manipulating and staring at a low fidelity model. And of course, this saves a ton of time by doing something like this. And now, of course, evaluating this dashed yellow line, the bifidelity curve, this guy has the same cost as this quartic polynomial, but I get similar accuracy to the high fidelity model. Okay, so that's kind of the selling point. This is one of my favorite examples because it shows that really the low and high fidelity models have, I mean, they're not conforming degrees of freedom. One's doing finite elements. One is just evaluating a polynomial. They're just very, very different, but they get you similar answers.
But you did have to evaluate the high fidelity model at some
Yes.
number of points, right?
Exactly. Yeah. So I used, so if I had an oracle to tell me what the most representative high fidelity parameter values were, then life would be easy because I would just go reconstruct those. But this procedure gives me a way to get something that substitutes for an oracle, basically. Right? I don't know.
Your final reconstruction is linear combination of the high fidelity samples you do, right?
Correct.
So basically, you're approximating that green curve by something that's like piecewise linear, or is that something like that?
It's not piece.
Oh, right.
Yeah, it's a
Least
finite element.
squares.
Yeah.
Yeah. Okay.
Yeah, it's least squares on the finite element mesh.
Okay.
So it's something. Yeah. And so I think what you're asking is, what are those C sub n coefficients? What do they look like? And they're implicitly defined through the least squares procedure. So we don't have an explicit expression for them, but they're not kernel functions. They're not Gaussian kernel functions. They're not piecewise polynomials. They're just some crazy looking functions. Okay. So with time left, I think we're going to skip very far. So please forgive all of this. But there's some theory is the point. And okay, I think this slide I just meant to point out, this is a 2D thermally driven cavity flow. We have a way of actually taking, okay, the real error, which I don't know how to compute, of this multi-fidelity estimator, but we have an error estimate that can get tighter if you're willing to invest more effort. So this R basically tells you how much effort you're willing to invest. And it looks like, yeah, I think these things are flipped. I think the top one should be R equals 30 and R equals 15. Anyway, so we have a way of estimating error. So this is practical in these cases. Yeah, that's fine. We don't have to talk about this.
Let me ask a little bit, and the bounds depend on, just guessing from the slide. So the bounds depend on how the high fidelity model changes as you use more points. Is that what?
Yeah, so essentially one, I think, nice way to look at how the bounds matter is that, okay, it depends on this thing epsilon, which is, so this is essentially a Gram matrix in the high fidelity model, which I don't have access to. And this is the Gram matrix of the low fidelity model, which is the one I'm using to select points. Mm-hmm. And the discrepancy between these is how you get an error estimate. Yeah,
so you approximate the high fidelity Gramian with a smaller number of high fidelity snapshots, and then.
Exactly. Yep, that's right. And this gives you a statistical estimate for what the real value of this thing is. Okay. And there are singular values of the low fidelity snapshot matrix involved, blah, blah, blah. So, okay, so you can do that. I'm going to skip to an actual interesting problem or an interesting application, I think. So here's the stenodic flow. It's okay. I'm really interested in maybe this one. So here's an example of design optimization. So what I'm actually trying to do is I'm trying to minimize something. I'm trying to minimize over a placement of mass, which I'm calling a row. So the game is, here's a domain. I'm trying to fill this domain with mass to make a structure like pictured here. And the reason I want to do this is I want it to be robust with respect to forcing on one end of the mass. Okay, so this is a topology optimization problem. What's the right way to distribute a fixed amount of mass inside this region so that it's robust, so that when I push and pull it in a certain way, it doesn't move, right? So I might be interested in this for building bridges, for example. Excuse me. And it turns out that, okay, here's an optimization problem, and this optimization objective function involves something called C of y, and this capital C is basically dependent on the solution to an elliptic PDE. Okay, so that's essentially the punchline. And so this is a design problem where the objective function depends on solving a PDE. Excuse me. So what I'm going to do is I'm going to, of course, you can imagine this is expensive because to solve a design optimization problem, I have to do, for example, gradient descent. That requires me to evaluate the objective function a bunch of times. That requires me to evaluate a PDE a bunch of times. So instead, I'm just going to replace this PDE with my multi-fidelity approximation. Okay, and when you do that, so here's a fine scale optimized topology. And as I move to the left, these are coarse inversions. So this is simply the result of what a low fidelity design optimization gives you, or a bit of a higher fidelity one. And the point is that if you actually use these predictions, so you actually use these predictions in a multi-fidelity situation, this is what the optimized design at the high fidelity level is, sorry. And the point is that it's basically the same as the high fidelity model, but all the analysis that I'm doing is on this with a small amount of effort that I invest in doing this. Okay, so I can really save a lot of time because I don't have to solve a bunch of PDEs like this. I can solve a bunch like this, which is a 16 by 16 mesh. So you can really get a lot of information from this. You can do this in 3D. So we did this in 3D for 3D topology optimization. So this is low fidelity, which is pretty bad. And here's the multi-fidelity reconstruction, and here's the high fidelity one. So they look similar. That's kind of the point. So I think this is probably a good point to just kind of wrap things up. So I know that I skipped a ton of things, but again, the main point that I was trying to address today is that one solution to multi-fidelity problems is with low rank methods. And naively, what we're trying to do is accelerate high fidelity simulations, high fidelity forward models. And the general idea for how to do that is that we're going to hope that the high fidelity model has low rank structure. If the high fidelity model has low rank structure, I claim that we can use coarsened low fidelity models to identify that low rank structure. And that's a lot cheaper to do because, of course, the low fidelity model is cheap. So once I analyze the low fidelity model with a bit of non-trivial effort, but you can do it, that gives me a strategy for how to do reduced order modeling at the high fidelity level. And that is, that's essentially the innards of this low rank multi-fidelity procedure. You do low rank approximation on the low fidelity model, and then you lift that low rank approximation to the high fidelity model. And you use that, and that's the multi-fidelity surrogate. I didn't show you any of this, but we do have sort of a priori convergence analysis, which is something you'd expect a mathematician to provide you, things that look pretty but are useless. Those are sort of the formulas in the a priori analysis. We also have what I'll call a posteriori analysis, which are actually practical error estimates that you can use to actually ascertain whether or not this is doing a good job. So this is not sort of a blind procedure where you just hope it does the right thing. We actually have metrics that can tell us whether or not it's doing something reasonable. So I think I will end there. So thanks for your attention, and yeah, it's my pleasure. If there are questions, I'm happy to take them. So.
Anybody else have questions? I mean, I can always ask questions, but. So one question is, your title had uncertainty quantification in it, and that was partly how I sold the talk. So how uncertain how that fits in?
So this is, well, I showed you, I think, this example. Sorry, let me find the right slide. So this is a canonical example in UQ. Sorry, I'll go back to the problem statement. This is where I have an uncertain diffusion coefficient, and I'm approximating the diffusion coefficient by essentially a random process, a finite dimensional random process. And actually what this error here that I'm showing you is an error in the standard deviation of the forward prediction, given the input uncertainty that the diffusion coefficient imparts, the random diffusion coefficient. So this is, this would be a forward problem in UQ. Even the design optimization, the topology optimization that I showed at the end, that was actually a problem from uncertainty quantification and topology optimization, because you have a load on a structure, and you want the design of the structure to be robust to, basically an uncertain load. And so the design objective that I showed on that slide was actually an objective designed. In fact, it's probably, I think the formula was there, I just didn't talk about it. Sorry, there are too many slides here. So this objective function is, it's called a robust optimization under uncertainty. So I'm trying to minimize both the mean of something bad and the standard deviation of something bad. So this is a standard robust optimization problem in UQ to try to design something subject to statistical constraints on the structure. So that's the connection to UQ, but you're right, I didn't actually say that.
So it's not the mean square? Looks like
Yeah, I think you're right. You're probably correct. Actually, what I probably believe is going on here is that we, of course, put a regularization parameter here, and this guy probably is meant to scale inversely with with that. So yep, good eye. You're right. Yep.
Anybody else?
So the E here is the expectation with respect to Y.
Yep. So I changed notation on you. Y here is the parameter, mu. So did that answer the question?
Okay, there are two directions of forces applied to the structure along the x direction and also the one along the y direction. So this optimization is for the y only. So you want to keep the y direction stable?
No. So yeah, this is just a slide with bad notation, or it's a slide with notation from a paper that's inconsistent with what I did here. So y here does not mean the y direction. Y here means the parameter. X is actually a vector. It's x1 and x2.
Mm.
And y is a parameter that yeah, we're varying along. And the parameter affects the forcing essentially. So and yeah, I guess even here I called it fx and fy, but this y does not mean. I mean, in this picture it means vertical direction, but you know, in the equations y here is the parameter. So I'm not taking an average over space. That's not happening. So, yeah.
Okay, so you also have interesting example of the uniformly distributed force along a beam, right?
Yep.
So in that case, the high fidelity model. So how do we get that from the finite element method?
Yes. So this is the beam example I think you're referring to, and this picture is the mesh used in a finite element simulation. That's the high fidelity model.
Okay.
And let's see here. I think the uncertainty here is in, so Q, which is the forcing, the uniform forcing on the top of the beam, is uniformly distributed. These E1, E2, and E3s are Young's elastic moduli of this beam, and so they are random in some regime. Yeah. So. And so the solution to this problem is another Laplace equation simulation in structural mechanics. So you can formulate this as a PDE with a finite element mesh, and you just hit go in a simulator, and it, you know, gives you an output. So.
Okay, anybody else?